Right, we're going to start off by looking at section 4.4, which is on radical functions. Basically just a fancy way of saying functions with roots, square roots, cube roots. We're going to do a little bit of algebra, like solving equations. And we're also going to look at what they look like. We're going to see there's certain patterns. So once you understand the pattern, they kind of look, pretty much all of them look pretty similar, depending on the pattern. So these are examples of different kinds of radical functions. Okay, the first one is a square root, x minus 2. That's something that we would draw. Okay, that's a pretty typical one. This cube root of x squared minus 1 plus x, it's a radical function, but a little beyond what we would sketch. If you made this exponent a 1 instead of a 2, okay, we could do it. And if you made this like a plus and make it a fixed number, like plus 4, then it would be something we would sketch. The way it's written, a little bit more advanced. So basically, any expression of the form nth root of something, as long as n is an integer and it's greater than 1. Right, so we don't really, when we're talking about radical functions, we don't talk about like a 2.5 root. There's no such thing. You can take a square root or you can take a cube root. There's nothing in between the two for radical functions. So no negatives for that number, and also no decimals. And so any expression of that form is called a radical, and the number that you put right there, that's called the index. So if I ask you for the index of a radical function, I'm just asking you what kind of root are we taking? Square root, cube root, things like that. Yeah?
The A is the radical?
The A is, well, I'll tell you in a second. The A is the radicand.
Which one's the radical?
This whole thing is called a radical. So any expression that looks like this, I would call that whole thing that's in the box a radical. Or you could say a radical expression. Then within that, there's certain parts. The index of the radical expression is the little number that's in like the V-shaped part. And then under that root symbol, that's called your radicand. So this is a radicand, x minus 2. X squared minus 1, that is a radicand. The actual check mark thing that has more of a horizontal line on the top, you can just call that your radical symbol, or radical sign. Okay, so you take a radical sign, you throw a radicand underneath it, put a number in for the index, and that's called a radical expression, or just a radical. Okay. Any questions on the parts of a radical expression? All right. You don't always see an index. Okay. In fact, the very first problem I gave you, there was no index. I could put one in if I wanted, and that means exactly the same thing as that. If you don't see an index, we always assume it's 2. In other words, you assume you're doing a square root. Now, sometimes, depending on what you're doing, it's helpful to take something that has a radical sign or symbol in it and rewrite it without it. Okay, and here's how you can do it. If you have a square root of something, that's the same as raising the x minus 2 to a certain power. Does anybody remember what power is equivalent to a square root? Yeah? Oh, it has something to do with a 2, but 2 would be squaring that. but it does have something to do with a 2. Yeah?
-2?
Okay, another good guess, not -2. That would cause it to flip. If you make an exponent negative, it would put it in the bottom, but there's only so many more options. I think we're getting there.
Is it 1/2?
It's the 1/2 power, yes. So if you have a square root, that's exactly the same thing as raising a number to the 1/2 power. Okay, you could just try it. Take the square root of 8, you get 2.828. Take 8 and raise it to the 1/2 power. You get exactly the same thing. All right. How about a cube root? Then you want to have a guess what exponent you can use in place of the cube root symbol? Yep. Yep, you could put 1/3. And how about in place of the 5th root? What fraction could you use?
1/5.
You could use 1/5. And this is probably, out of all these examples, the only one you'd really want to do that with is this one. Because you can simplify the 5th root of x to the 4th. So that's x to the 4th. And instead of the 5th root, we raised it to the 1/5. But what can you do when you have a power to a power? You can take those two powers and do what with them? Yeah, Chris? You can multiply them together. So 4 times 1/5 is 4/5. So that last one, that's the reason why you might want to change something to a fractional exponent. Because it might simplify with another exponent. Okay. Questions on rewriting something that has a radical sign to rewriting it so it has a fractional exponent? And I think after the first couple, people seem to kind of get the pattern. It's just 1 over the root. So if you were doing a 12th root, 1/12th power. 20th root, 1/20th power. Okay. All right, so when they ask us to solve an equation for what's called the principal root, okay, equations with roots usually have more than one answer. When they ask for the principal root, that means they want one answer, just one. So for example, if I asked you what the square root of 4 is, there's 2 answers, 2 and -2. Well, which one is the principal root? I'm going to show you right now. Well, there's 2 cases. It depends on if you're dealing with an even index or an odd index. If you're dealing with an odd index, you want to think of basically solving this equation. Right? And I'll give you an example with numbers, and if it doesn't make sense, I think it will when I throw some numbers in there. So let's say you were trying to find the cube root of 64. The way you figure out the cube root of 64, okay, in your head is basically ask yourself, what number would I raise to the 3rd power and get 64 as the answer? That's what I would think of in my head when I try to find the cube root of 64. What number to the 3rd power gives me 64? So I've got my x, that's my n, and what's underneath? That was my a. And I just basically plugged them into that formula. So in that case, what would the answer be? Yeah, like 4. Yeah, they don't always come out nice, but just to show an example, I picked one that came out nice. Right. Now, what's a little different between odd and even roots is I could ask you something like this. Let's do another odd root. Let's do the 5th root of -32. All right, so when I want to find the 5th root of -32, I'm trying to think in my head, okay, what number to the 5th power gives me -32? Even if you can't figure out the number, what do you know about the type of number it has to be? something to the 5th power gives me negative 32. Yeah?
Has to be a negative.
It's got to be a negative number. Okay? So, big difference here in what I'm about to show you is the answer to an odd root can be negative. In this case, it's negative 2. Negative 2 times negative 2 5 times will give you negative 32. Now, when you're dealing with an even root, square root, fourth root, anything like that, you have to have a number under the root sign. Okay, the radicand has to be greater than or equal to 0. It cannot be a negative number. If I put a negative number as the radicand in an even root, what kind of answers do we start to get into? Like if we take the square roots of negatives or fourth roots of negatives, what starts to happen?
With the eyes.
Yeah, we start getting into imaginary. Okay, we're not going to focus on imaginary. Okay. So if you're dealing with an even root, I'll always give you problems where the radicand is greater than or equal to 0. You tell me the answer that's the non-negative number. I won't say it's always positive, because I could ask you a question like, what's the square root of 0? The answer is 0. It's not a positive answer, but it's not negative. Any question on what they're asking for if they ask for the principal root? Principal root, single answer to the problem. Now, if we were going to get into imaginaries, basically what ends up happening is whatever root you're taking, there's that many answers. So if you're doing a square root, there's 2. Cube root, there's 3. But what starts to happen is we start getting into some real and some imaginary. All right? So at some point we'll come back to that. But for now, we're just going to focus on this. Okay, so what I want to look at is specifically just a square root. And I want to try to answer the question, what happens when you take a square root? Does the number get smaller than what you started with, or does it get larger? Let's start with this one. So x is 4. Justin, what's the square root of x?
Oh, 2.
2. So in that case, the number got smaller. Okay. Square root of, let's try this one. 18. Square root of 18, if you were going to write it, reduce it, it would be 3 square roots of 2. But I actually want to see, is that smaller or larger? Smaller. Okay, 4.24. So Natalie, so far it seems like when you take a square root, the number, what happens to it? It gets smaller. All right, let's try this one. 1. Kathleen, what's the square root of 1? 1. Well, now it didn't get smaller. That time it stayed the same. So maybe the pattern is when you take a square root, it either stays the same or gets smaller. Okay, that's what seems to happen so far. But let's try this one. Square root of a half. Okay, square root of 0.5. Put in 0.5, take the square root, I get 0.71. Gabe, what happened that time? Got bigger. Okay, so maybe it gets bigger, maybe it gets smaller, maybe it stays the same. Now we've seen everything.
So wouldn't it just be the square root of a number greater than 1 is larger, and anything less than 1 is...
When you take the square root of a number bigger than 1,
smaller.
It gets smaller, yeah.
And then anything less than 1 is larger.
Yeah, so we want to, we're going to kind of describe that pattern. When does taking a square root get larger and smaller? We're going to look at it as a graph. But that's exactly it. Take the square root of a number bigger than 1, it gets smaller. Take a square root of a number between 0 and 1, it gets larger. Exactly 1 stays the same. Right, so let's graph a couple roots with even indices. Again, you can really just watch me do it. Let's see what happens. What I want to focus on is which graph is on top of what. Okay, I want to see, is the square root above it, the fourth root, or is the fourth root above the square root? Let's kind of see what happens. And the answer is it's going to be it depends. Because at 1, there's this kind of behavior where things start switching. Okay, they change from whatever you were doing before to now something different. To type in a fourth root, you just plus 4. You go to math, and then the fifth option down, and it'll change that to an index. And we type in a sixth root, 6, math, fifth option down. All right, I'm going to start with the standard window, but it's going to be helpful to zoom in a little more. Okay, there's your square root. There's your fourth root, and there's your sixth root. It's kind of hard to see what's going on, but everything's in quadrant 1. So why don't we set it so we're in quadrant 1, and let's set our y max to 4. Because if in this window, nothing goes higher than 4. All right, so no negative there, no negatives there, and let's set the y max at 4. Now we should be able to see it a little clearer, especially if I make it bigger. All right, let's take this and look at what's happening. So the blue graph, that was the square root. Let's just write down what they, you know what, just go like this. Okay, so the blue graph was the square root, the red graph was the fourth root, and the black one was the sixth root. When is the square root on top of everything? How would you describe when that happens? Yeah?
When it's greater than, or not when it's greater than 1.
Yeah, when it's greater than 1, it seems like the square root is on top of everything. How about when you're less than 1? What happens to the square root then? Yeah.
It's below everything.
It's below everything. So it's at 1 that it switches. In fact, all of these graphs go right through the point 1, 1. That's something we're going to write down in a second. 1, 1 is a point on every even graph, unless you shift it. Like if you shift this up or down, that would change it. But without a shift, all the basic graphs go through 1, 1. And the pattern is with even roots, as you take bigger and bigger indices, if your number is bigger than 1, it gets smaller and smaller. All right. So a square root would always be above a fourth root. A 10th root would always be bigger than a 20th root. All right. So the smaller the index, the bigger that it stays when you're after 1. When you're before 1, that all switches. All right. The smaller your root, like very, very small index, results in a very small graph. It's below everything. If you get a larger index root, larger index, it will be above everything between 0 and 1. Okay? So actually, I mentioned the second point. 1, 1 is a common point to all the graphs. So is 0, 0. It's hard to see, but they all start at 0, 0. Just ask yourself, what's the square root of 0? 0. What's the fourth root of 0? 0. The domain, when I showed you kind of the big picture before I changed the window, everything was in quadrant 1. It never went left of the y-axis, which means the domain is from 0 up to infinity. So the domain starts at 0, heads to the right forever. How about your range? The blue, the red, and the black graph all have the same range. What's the lowest they go? And then what's the highest? Okay. It's also 0 to infinity. They start right at the origin, and they're going to keep going up forever. it looks like they're leveling off, but they never do. Okay? They still curve up slowly forever. And if you're not sure that doesn't make sense, well, ask yourself, if you take the square root of a bigger and bigger number, does the answer ever stop going up? Like square root of 1,000,000, square root of 2,000,000, square root of 3,000,000. The answer just keeps going up. It never stops going up. Okay, and then this is describing which graph is on top in certain sections. So if you're between 0 and 1, the square root is less than the fourth root. The graph in blue is under the graph in red. You want to see it as colors. That was blue. That's red. And that one was black. So the blue graph is less than the red graph. The red graph is less than the black graph, between 0 and 1. When you're more than 1, it all reverses. The blue graph is above the red, and the red is above the black. Any questions on the patterns there with even roots? Okay, so next we're going to take a look at odd roots. Okay, odd roots are a little different. When I give you a number for x right there, what kind of number does it have to be based on the domain? It's got to be positive. That's not true with odd roots. I can have you take a cube root of a positive, cube root of a negative. I can have you take the cube root of 0. You can plug in anything for a cube root. So what that means is on our graph, it's not just going to go to the right, it's going to go in both directions. So for this one, I'm just going to graph 2 of them. I'll graph the cube root and fifth root. Let's change that to a 3 and a 5. Okay, let's see what it looks like. I'll start with zoom 6, but I might have to zoom in a little more. Okay, right away you see a huge difference. It's going left and right. But what I want to focus more on is what's happening in here. Can't really tell from that window, but I want to kind of look at which one's on top of which one. So let's set the y max. Let's go -3 to 3. So we'll zoom in on that section right there. And I think between that and me making it a bigger picture, you'll be able to see what's happening. Now, one thing that's happening is it's getting so steep in the middle, the calculator can't even really connect it. It is connected. It should be connected. All right. I'm going to zoom in even more. Let's go -3 to 3 on the x-axis. That's better, but I still don't think you can really see what's going on. Okay, I think that's good enough. So let's take that and look at it. Okay, so how many sections is the red graph on top of the black graph? Yeah, Ben? 3 sections. Yeah, I think it looks like 2. I see 2 sections where the one in red is above the one in black. How about the reverse of that? How many sections is the one in black above the graph in red? In 2. So it seems like things kind of switch places right there. Graph in red goes from below to above. And then it switches again. Let's see.
1 and 1.
Yeah, it definitely switches again right there. The graph in red goes from below to above. And then I think they switch places right there. The graph in red looks like it's above between 0 and 1. And then below between 1 and 0. So these kind of switch places a couple times. So let's describe what's going on here. So there's 3 points that are common to all odd radical functions. -1, -1, 0, 0, and 1, 1. And I've marked them all on the graph right there. Okay, domain. How far left and right does it look like the graphs in red and black? There you go. Yeah.
Negative infinity to infinity.
Yeah, negative infinity to infinity. And that's also true for the range. Negative infinity to infinity. I just want to make sure I wrote something down on the other one. Yes, I did. Okay. So domain and range, both negative infinity to infinity. So now we can describe what's happening. You really have 4 sections. You've got the section that's less than 1. You've got a section between, less than -1. So you got, just put in like dotted lines. You got everything to the left of that dotted line. So we'll call that section 1. You got section 2, which is everything between -1 and 0. Section 3, which is everything between 0 and 1. And then section 4, which is everything from 1 to infinity. Okay, it's not super critical that you remember, wait, okay, we're between 0 and 1, we got an odd root, so that means, all right, that means this one should be on top and this one should be below. It's not really super important. I just want you to see that they cross each other a couple times. Okay, so if you're in the less than -1, which is this section, or between 0 and 1, which is that section, the cube root is under the 5th root. Okay, the graph in red is under the graph in black. And if I did a 7th root, I could put in something like this. The 7th root would be underneath the 5th root. So it would be even lower than the one in black. Okay, this pattern just continues. Now, if you look at the other 2 sections, sections 2 and 4, it switches. Okay, that's where the cube root is above the 5th root in sections 2 and 4. So graph in red is on top. So any questions in general about what an odd or what an even root looks like? They all pretty much have that pattern. Sometimes the S shape is a little bit more compressed or stretched or shifted. But odd roots always look like that. Even roots always look something like that. All right. So transformations. There's 4 transformations, 4 main categories you can do. You can shift left and right. That's what A would do. So if you want to write that down, you can, but it works the same as all transformations we've studied all year. The stuff inside the function is always your horizontal stuff. The stuff outside is always the vertical stuff. Horizontal always does the opposite of what you would expect. Vertical does exactly what you would expect. So A is a horizontal shift. Positive is going to move it left. Negative is going to move it right. It's the opposite of what you would expect. Hey, how about B? We're still inside the function, so we're still horizontal, but does anyone have a guess what B would do? It's not a shift. What else could it be?
Stretch.
It's a stretch. All right, and it's the opposite of what you would expect. So bigger numbers are going to compress it. Take a really, really, really big number, it's going to compress it. take a small number. By small number, I mean a number between 0 and 1. That's going to stretch it. The smaller the number, the more stretch you get. So it's the opposite of what you would expect. So that's B. C and D are your vertical stuff. C is multiplication, just like B was multiplication. So C is going to be what kind of transformation? A shift or a stretch? Stretch. It's going to be a stretch, and it's exactly what you would expect. A big number stretches it bigger, a small number compresses it smaller. The bigger the number, the more the stretch. The smaller the number, like 0.2, that's going to compress it a lot. And then D, that is a vertical shift. Okay. Adding or subtracting is always a shift. Multiplying is always a stretch. And this is exactly what you would expect. Plus a number shifts up, minus a number shifts down. Now, if C or B were negative, that causes something else to happen to the graph. Does anyone remember what happens if one of those numbers is a negative? Emily? It flips it. So the two kinds of flips you can have are flip over the x-axis or flip over the y-axis. Right. If you had something like this, besides the horizontal shift and the vertical stretch, this negative, it's with the vertical. So I think of it in my head, okay, that's a vertical flip. So if I want to ask myself, what axis is that over? Vertical means up to down. So if I had a picture like this, it would end up looking like that. A vertical flip is over the x-axis. So a negative here causes a flip over the x. A negative here, well, that causes a flip over the y. It's a negative with the horizontal stretch number. Since it's with the horizontal, it's a horizontal flip. A horizontal flip would look like this. That's a horizontal flip. Left to right, it's over the y-axis. So negative inside here, flip over the y. Negative here, flip over the x. It's exactly the same as all the transformations we've done all year. There's no changes at all. That's what I just said right there. So let's look at these graphs and I want to know what I would have to do to the parent function, like the most basic square root graph, to get this graph. Right, so I could start out with, to get g of x, and now I just have to explain what I would do. What would you have to do to the square root of x to turn it into g of x? Yeah?
Shift it to the left.
Shift it to which way?
To the left. Or to the right.
To the right. Yeah. So we always look at the number after the minus sign. That's how I think of it. And I say, okay, if I block everything before that number, I have a positive 2. It's going to shift it right. So it's going to shift right 2. Or just get used to looking at it and say, okay, if I see the minus, I know it shifts right. If I see a plus, it would shift left. So shift square root of x, right 2. All right, how about this one? How would I get h of x? Yeah, Kathleen? So we're going to shift square root of x, left 3. Nothing too fancy. They each were just a single step. Let's add a little bit to this one. Let's put a 2 in front and let's make a minus 5 there. Okay. Before I even deal with that other stuff I added, there's something kind of wrong with how the radicand is written. How do we usually like to put the radicand? And if you're not sure, just look back up at my template. Okay, my template doesn't look like this. Yeah.
The X comes first.
The X should come first. So can you tell me, Allison, how I would write that with the X first?
Negative X plus 3.
Yes. Now, before I even describe the transformations, can anyone tell me how many things are going to happen to the square root of X to turn it into that? Yeah. Let's see. 1, 2, 3, 4. Yeah. So to get K of X, do the following to square root of X. And you always want to list them in the order that I use the letters. A, B, C, and then D. All right, so first one. What would be the first thing that I would do? Well, yeah, right?
Horizontal shift left.
Yep. So we're going to say shift left, and then you just have to tell me how much.
By 3.
Yeah, shift left by 3. So shift left 3. If you say shift horizontally left 3, that's fine. But if you say left, I understand that it's horizontal. Just don't say shift 3. Then I don't know what you're talking about. All right, so shift left 3. What's the next thing we would do? There's really, this is like a negative 1x, if you want to think of it that way. Yep.
You flip the graph over the y-axis.
All right, so I always have to think about it for a second. So that's the horizontal. It's a horizontal flip, which means it is over the y-axis. Yep. Flip over y-axis. Okay, I'll do the next one. That'd be a vertical stretch by a factor of 2. Factor of 2. And the fourth thing, what would be my fourth thing I would do? Yep, Kaya.
Shift to the left 5.
Well, we already handled shifting left and right. So that minus 5, that's outside the function.
Or shift down.
So that's going to be down 5. Shift down 5. So these two transformations both affect your x values. These two transformations affect your y values. So basically, if you gave me a coordinate, I could follow these steps and figure it out exactly where it would end up. If that was a graph on the original, 4, 2, x is 4, the square root of 4 is 2, I could go through all these steps. Okay? Take the x value and subtract 3 from it. Take the x value and make it the opposite. Take the y value and double it. Then take that result and minus 5 from it. And that would tell me exactly where this coordinate would end up if I did all those transformations. All right, so when we're sketching radical functions, one important point we always want to find is 0, 0. Okay, if I go back to the sketches, 0, 0 is on both. But the difference is sometimes 0, 0 is what I call a center point, and the graph is going to go out in each direction from there. Or sometimes 0, 0 is a starting point, and the graph goes in one direction. So it depends if it's an even or odd. But either way, whether it's an even or an odd graph you're trying to sketch, find the center point or find the starting point. So the way we can figure out where the starting point is going to be if we shift it is basically set the radicand equal to 0 and solve it. So if you had something like this, that's That's an even index. So if you wanted to figure out where that graph is going to start, just set 3x plus 4 equal to 0. And solve. So the graph would start at negative 4/3. Now, once you know the x value, if you want to find the y value, all you have to do is take that number, remember, because it's like y equals, plug it in for x, and there's your y value. So just use substitution, plug it in. After you've done enough of these, you start to see a pattern. And you don't even really have to do substitution, but you'll probably see the pattern after the first couple. All right, so now that gives you either the location of the center point for an odd index or the starting point for an even. Now, we want to check some other points. This is where I would use the table on the calculator. So I say you want to check points to the left and the right of the point you found. Now I said if applicable. How come? How come you might not always be checking points on the left and the right? Yeah?
Because if it's a starting point, it's not going to have points to.
Right. If it's a starting point, it's going to just go in one direction. Maybe it goes like a standard one this way, or maybe it goes the other way. It depends if you flipped it or not. I think usually 4 or 5 points is sufficient to get a good graph. Okay, so let's try to sketch this. I know it's not written in the standard format. It should be negative 2x plus 3. And if you were describing transformations, maybe you'd want to do that. But to sketch it, it's fine like that. So first of all, is this graph going to have a starting point? Or is we going to be finding like a center point? Oh, Joe? What kind of point are we finding here? Like a starting point or a center point?
Starting point?
How come?
No.
Anyone help him out? Yep.
A center point because the index is odd.
Exactly. Center point because the index is odd. So, first thing I want to find is my x value. Well, I guess one way I could do it is I could list out all the transformations and just do the transformations to the coordinate. But it's probably easier to just use algebra like I explained. So what am I going to do with the 3 minus 2x? Just set it equal to 0. So we're going to get... wait a minute. I'm going to get... Let me do this one step at a time. So you get 3 equals 2x, and we get 3 halves. So there's the x value of your starting point. How do we get the y value? Yeah?
You plug in the x value.
We plug it in. Now, when I plug it in for x, I already know what I'm going to get when I do that all out. When you plug in 3 halves for x, what do you get for the part that I circled? 0. We already know that. So really, you don't even have to waste time with that. That's 0. And what's the cube root of 0? 0. Now, the only part we have to look is the stuff outside. And even more importantly, really, we only have to look at that. Because if you take the cube root of 0, which is 0, and double it, what's 0 doubled? Still 0, plus 1. That's the vertical shift. Okay, so that's the part that becomes important. So your center point is 3 halves, comma, 1. Okay, so let's make a quick sketch. Let me... I don't know, I won't stay where I want it to stay. So I'll just put that there and then that. Alright. So 3 halves, comma 1, that's about 1.5, comma 1. So there's that. And now I could use, I could do this by hand. I'm going to pick probably 3 or 4 more x values. But it's probably easier to use the table. So you gotta be careful when you type this in. And I know we normally don't use the multiplication sign, but you're gonna have to here. Because if I don't, because I want 3 to be an index. So I have to do 2 times 3 just to separate the 2 off. Now I can do math 5, and it just puts the 3 as the index. When you type it now, you could get rid of that sign. You don't need it now. Although to me it does look a little confusing. It kind of looks like 2 cubed. The calculator wouldn't do it that way. So I would just leave the multiplication in there. So 2 times the cube root of 3 minus 2x. And then plus 1. Okay, I might check the center point just to make sure we got it right. Let's go second table. Well, looks like it's at 1.51, but I'm going to just check it with the table. Yep, so that's the center point. And let's pick a few values that are smaller. The intercept is always nice. Let's go -5, -10, +5, +10. I think that's plenty. If you want to do more, you can. All right, so we got 0, just a little less than 4. All right, -5, we're at 5.7. 3, 4, 5. 1, 2, 3, 4, 5, 0.7. And -10, we're at a little above 6.5. 1, 2, 3, 4, 5, 6.5. All right, so I can see that part. And now 5, I'm at almost -3. 5. And 10, I'm at a little more than -4. Or less. 2, 3, 4. All right, there. That's pretty good. Now just connect that. Not perfect, but it's pretty close. And here's your sketch. Okay, so odd root goes in each direction. It's going to go down and up forever. It's going to go left and right forever. Any questions on that one? How about any questions on how you would do an even root? It's pretty much the same steps. You would start by getting your starting point, which in this case would be 4/3, and your y value would be -2. So once you've got your start point, pick some values that are smaller than 4/3, pick some values that are bigger than 4/3. Well, actually, what would I want to be careful about here? I kind of fell into the pattern of the last one, but this is an even root, so what does that mean? Yeah?
But there's no other thing.
It's only going to go in one direction. So make sure you're not taking the 4th root of a negative number. So to avoid that, you could let x could be a really big negative number. Think if it was like -50. -50 times 3, -150. 4 minus -150 is a positive. So this graph is going to go to the left. The other way I can tell it's going to go left is you've done a horizontal reflection. Normally graphs go like this. That negative is going to flip it the other way. So you're only going to be checking numbers smaller than 4/3. If you plug in a number bigger than 4/3, like 2, you run into a problem. 3 times 2 is 6. 4 minus 6 is -2. It's no good. Okay, so it only goes in one direction. Okay, so the last thing we'll look at, which doesn't require any graphing at all, is how you solve a radical equation. So in order to solve a radical equation, you have to isolate the radical on one side. And then you get rid of it by raising it to the power of the index. So if you were doing a square root, that has an index of 2. I would cancel out a square root by squaring, raising to the power of 2. If I had a cube root, I would end up raising to the power of 3. Now, to solve algebraically, it gets really messy really fast. So all the problems I give you are going to involve, well, if they have anything complicated in them, square roots. It's cubing or fourth powers. It involves a lot of foiling, and that can get pretty bad if you've got to foil something with roots out like 5 times. That just takes a while. Okay, so most root problems, I would expect them to be square roots, unless it's a really, really, really simple one you can do in like 1 step, then it might be a cube root. We always want to check for extraneous solutions. Remember, that means it's an answer that works because of the algebra you did, but it doesn't work in the original problem. What would be extraneous in this case? Well, if you were doing a square root problem and you plug x in, and x causes you to take the square root of a negative number, that'd be imaginary. So that would be extraneous. Okay, so check for things like that. Okay, let's try this one. Now I said here, sometimes you might have to raise each side to a power to cancel a root twice. And here you're going to have to do it twice. So the first step is to get one of the radicals by itself. Doesn't matter which one. Let's say I want to get this one by itself. How would I move the negative square root of 4x plus 9 to the other side?
We just add square root of 4x plus 9.
Yeah, we'll just add it. Move it to the other side. So we get square root of 6x plus 12 equals 1 plus the square root of 4x plus 9. Now we're ready to get rid of one of these roots, the one that's on the left. Okay. I have square root. What power would I raise to cancel square root out? Go out, chart.
You'd raise it to the second.
Yeah. And this is where you just have to be a little careful. The left side is simple. Square root, square. Left side is done. It's just 6x plus 12. But the right side, you cannot square individual terms. You have to square the whole side, which means FOIL. Okay, so what you really have on the right side, if you need to see it written out to do FOIL, is you have this. 1 plus the square root of 4x plus 9. Okay, so let's FOIL it out and see what we get. 1 times 1 is 1, plus 1 times the square root of 4x plus 9 is just 4x plus 9. But then I have another 1 times the square root of 4x plus 9. So how many square root of 4x plus 9s do I have? 2 from the outer and the inner distributive property. So 2 square roots of 4x plus 9 plus the square root of 4x plus 9 times the square root of 4x plus 9. Well, that's like saying this. The square root of 4x plus 9 times the square root of 4x plus 9 is the square root of 4x plus 9 squared. And Jacob, what would happen there?
That would just be 4x plus 9.
It would just be 4x plus 9. Now we have a lot of things we can combine and move to one side, because now my goal is to get this by itself. Okay? The first root you get rid of is always the hardest. The second one is going to be much easier because we're only going to have one left. So we've got, let's see what we've got. Let me write it out. So 6x plus 12 equals 1 plus 2 square root of 4x plus 9 plus 4x plus 9. Okay, what I'm going to do right away, I have a 1 and a 9 on the same side. When I combine them, what do I get? 10. So I'm just going to cross this out, and just put plus 10. Now I want to move 10 over to the other side. So how would I move the 10 over? Yeah. I'm going to subtract 10. Subtract 10. What else do I want to move? I want to move the 4x over as well. So how would I move 4x? Yeah. Subtract it. And subtract it. So we just canceled out a lot of stuff on the right. So I have 2x plus 2 on the left equals 2 times square root of 4x plus 9 on the right. The radical still isn't by itself. I want to get rid of that 2 in front. So Madison, how would I get rid of this 2 in front? Well, right now we have multiplication. It's 2 times something.
Divided.
Yeah, we divide it. So if you've got 2 times, doesn't matter what's in the box. If you want to get the box alone, divide by the number in front of the box. So divide by 2. And remember, we have to do it everywhere. Here, here, and that's all one big term, because it's all multiplication. So, those cancel, those cancel, those cancel. So now, x plus 1 equals the square root of 4x plus 9. So from what I started with, say I kind of started with something that looked, not that nice with 2 roots. Now I got it down to something with 1 root. It's a lot easier to work with. What would I do on both sides again now? I would have to square them again. So sometimes you have to do it twice. If you have 2 roots in the problem, you're going to have to do it twice. So square it, square it, square and square root is gone. Okay, Tori, if I square x plus 1, what do I get?
X squared plus 1.
Part of it. Plus 2x. Now from here, it's just a quadratic. So you can factor it, use quadratic formula, whatever you need to do from there. So x squared minus 2x, let's see, minus 8 equals 0. Okay, and if we try to factor that, let's see what happens. We're going to need a plus and minus. We're going to need a 4 and a 2. Let's see if that works. X squared minus 4x plus 2x. Yep, looks good to me. So what are my 2 answers for x? Yeah. -2 and 4. Now we just have to make sure that we don't end up doing something we're not allowed to do. Let's try 4 first. All right. 6 times 4 gives me how much?
24.
Plus 12?
36.
And the square root of 36? 6. Minus. 4 times 4 is 16 plus 9? 25. And the square root of 25? 5. 6 minus 5. Does that give me 1? We're good. So that answer is fine. Let's check -2. 6 times -2. -12 plus 12 is 0. Square root of 0? is 0. And then what are we checking? Negative 2. 4 times negative 2. And then if we add 9 to that, 1. Square root of 1? 1. Is 0 minus 1, 1? No. So negative 2 is extraneous. There's no way we could have avoided it. It's just that's what happened in the problem. Okay. So the only answer here is 4. Okay, let's try this one. So it's a cube root, but notice there's only one root in the problem. So you're not going to have to raise each side to a power twice, just once. And Chris, what power am I going to raise each side to?
To the third.
To the third. No. So x squared minus 2x plus 2 equals x cubed. Now that's a cubic, that's not a quadratic, so you can't use the quadratic formula. You can't factor it quite like I did the other one. But let's move everything to one side and get it equal to 0. Okay? And I always like the highest degree term positive. So I'm going to put everything on the right. What kind of factoring could I try here? Anytime you have 4 terms. And if you're lucky, it works out nice. Yep. Yep, we're going to try factor by grouping. And we're going to hope when we factor out what the first 2 have in common and what the last 2 have in common, we get the same thing. I see an x squared common to x cubed minus x squared. If you factor it out, that's you get x minus 1. What could I factor out of the second set? I think I can make this work to get x minus 1 there too. Negative 2. If we factor that out, negative 2x plus 2, perfect. Now, what factor is repeated?
I just have a question.
Yeah.
So, in the 0 equals x cubed minus x squared minus 2x plus 2, wouldn't that be plus 2x minus 2 because you have to subtract them with the other side?
Let's see, did I move them wrong? It's going to change the sign if I did. So it would be a plus 2x. Yeah, plus 2x minus 2. So that's going to change the sign on what I factored out to be, does that work now? I had the wrong sign on both. Plus 2x minus 2. Thank you. Okay, but we're still okay now. Now, what does each term have in common now? Justin.
X minus 1.
Yep. So let's factor that up. Okay, Robin, if I factor out an x minus 1 from the first term, what am I left with?
You're left with, if you're left with the negative 1, right?
From this term.
Oh, 1.
1. Think about what I would have to put right here so that if I multiply this times that, I got what's in the box up above.
X.
It's basically just the other term that's in the box.
Plus 1? No, minus.
Yeah, help her out.
X squared.
X squared. Because if you multiply this times that, you get that. So we have x squared plus, and if you factor an x minus 1 out of here, what would you be left with? Yeah, 2. All right, let's solve it and see what we get. X equals 1. Now, for this to be 0, what kind of number would you have to plug in for x?
Negative.
Well, negative squared is still a positive. And then a positive plus a positive is never going to be 0. Yeah? It would have to be imaginary. So you're not going to get any answers from there. The answer would be the square root of -2, or I square root 2. So we don't want imaginaries. So the only answer here is 1. If we check it, that gives me 1 minus 2 plus 2. That gives me the cube root of 1, which is 1 on the left. If I plug 1 in on the right, I get 1. It works. 1 equals 1. Any question on that one? So, a little different because you had to use factor by grouping, but I don't think it was as bad as the last one because you didn't have as much FOIL. Alright, so homework tonight is on page 255. There's a couple ranges, but most of it is just single problems. So 1, 3, 5, 6, 12 to 14, 20 to 22, and 28, 31, 35.